So all of the ions that we have learned to name so far have what is referred to as monatomic ions. They're just a single atom that is either lost one or more electrons or gained one or more electrons. So these are all monatomic ions. What we're going to learn about now are polyatomic ions. And polyatomic ions are groups of atoms, that's why they're called polyatomic, that are held together via covalent bonds that have either lost or gained some electrons, so that they have an overall electrical charge. If the group of atoms has gained some electrons, they'll have a negative charge, and if the group of atoms has lost some electrons, they'll have a positive charge, just like monatomic ions. So, a polyatomic ion is formed from a group of atoms held together by covalent bonds that has lost or gained one or more electrons. There are a handful of common polyatomic cations, and these can substitute anionic compounds for metal cations. So the common polyatomic cations are the ammonium ion, the mercury 1 ion, and the hydronium ion. In Chemistry 139, we probably won't see these last two. So something for you to be aware of is that the ammonium ion can substitute for a metal cation in an ionic compound. So previously we had said that ionic compounds can be recognized because they begin with metals. We should add to our list that they could also begin with NH4+. So that polyatomic cation can substitute for a metal cation. Okay. It's important to recognize that there are a lot of polyatomic anions. Many of them you can see here contain oxygen. These are referred to as oxoanions, or some people will say oxyanions, or if you're like me, you'll flip kind of seamlessly between the two. There is no difference. So most polyatomic anions, as I mentioned, are what we call oxyanions that contain a central nonmetal atom bound to one or more oxygen atoms. So what we're talking about is we're going to have some metal atom in the middle here, and then they have, just like my first example there, they have a bunch of oxygens connected to them, and they're anions, so they have some kind of negative charge. So frequently a single central nonmetal atom will form several oxoanions, and perhaps a famous example of this is how chlorine forms a collection of 4 oxyanions, where we have from 1 through 4 oxygen atoms connected. Okay, so here we go, we've got chlorine with 1 oxygen and a single negative. It's called the hypochlorite ion. Chlorine with 2 oxygens connected has a single negative. It's called the chloride ion. 3 and then 4 and so forth. Okay, so how do we know the names of these things? Well, the important thing to recognize is that there are no hard and fast rules for polyatomic ions. So the best thing to do is to find a web page that has a nice extensive list of their formulas, charges, and names, and make sure you've got it bookmarked. Now, there are a few sort of guidelines that can help us remember the names of some of the common oxoanions. So if you have a family of 2 oxoanions, and a good example of this is nitrogen, where nitrogen will form NO3 minus, essentially like that, and it'll also form NO2 minus, When you have two, the ion that has the most oxygen atoms is named by giving the nonmetal's root name, and then finishing that off with 8, and then following up with the word ion. So it becomes nitrate ion. And then the ion, in this case NO2-, that has the least number of oxygen atoms, you begin with the nonmetal's root name, so NITR for nitrogen, add the ending ITE, and then follow it up with the word ion. So your 8s will have more oxygens than your ites when you have a family of 2. Now, it doesn't always have to be 3 and 2. It sometimes is 4 and 3, for example, okay? Or it could be, 1 and 2, but it's just a matter that there's going to be one with more and one with less. Okay. Sometimes there are 4 oxoanions in the family, and the example that we gave was chlorine, which forms a series of oxoanions with 1 through 4 oxygen atoms. Now, this kind of gets complicated, so we're going to start with the one that has the most oxygens and work our way down. And for the one with the most, it goes like this. It goes per, then you put the stem, then you put 8, and the word ion. So for this guy here, this would become per-chlor-8 ion. So then you're going to go to the one that has the second highest amount of oxygen atoms. So in our example here, that's ClO3-, and that becomes a little easier. You just do the stem, and then the ending 8, and the word ion. So now we're at the one that has it's the third highest number of oxygen atoms in the list, and in our example that would be ClO2-, and then that becomes the stem with the ending ITE and the word ion. So, and then finally you got the one that has the least number of oxygen atoms, and then that becomes hypo, then the stem, then the ending ite, and the word ion. So in our example, ClO-, that would become chloride ion. So the sequence when you've got a family of 4 is that it goes per the stem name 8, then it goes the stem name 8, then the stem name ite, then hypo, the stem name, and ite. When you have only 2, it goes, the one with the most oxygens is the stem name and then 8, and the one with the least is the stem name and then ite. Now that's pretty complicated. You will eventually pick it up after a year or 2 of studying chemistry, but what I would recommend when you're beginning now is, like I said, just find a web page that has a nice extensive list of the names, formulas and charges of polyatomic ions, and bookmark it so you can look it up when you need it. You'll kind of learn it just by it rubbing off. Okay, so here's a whole bunch of them, and I've highlighted the oxoanions that belong to those families in different colors, so you can see those rules kind of playing out. So ammonium ion is probably the only common polyatomic cation that we're going to be encountering at this point. Hydroxide ion, very common polyatomic anion. Nitrate ion, nitrite ion, forming a family of 2 oxoanions. You'll see that the 8 has more oxygens than the ite, so you can kind of think of the 8s are bigger because they ate the ites. So then we have the series of 4 oxoanions of chlorine, ranging from perchlorate, chlorate, chlorite, hypochlorite ion. And then we've got chromate is very common, CrO4 2-, and then dichromate, Cr2O7 2-, also quite common. Really brightly colored compounds, these ones that contain the transition metals here. Carbonate ion, important in regulating the pH of blood and the ocean and other natural aqueous solutions of water. Sulfate ion and sulfite ion, again, you see the same thing, a family of two. The 8 is bigger than the ite. And then permanganate, another brightly colored metal containing polyatomic anion. Okay, so what do I want you to know? Well, there's 10 common polyatomic ions that we need you to know the formula for formulas, names, and charges for general chemistry. The important thing to recognize is they don't really follow any hard and fast rules like we were seeing for the monatomic ions. So the best thing is, like I said, find a list of these, refer to it extensively, and you'll slowly pick these up as you move through the sequence. Well, we've talked a little bit about this previously. When you write the formula for an ionic compound that contains more than one of a polyatomic ion, you need to put that formula of the polyatomic ion in parentheses, and then you write the as a subscript after the closing parentheses the multiplier. So just kind of keep that in mind, and then that acts to multiply everything that is inside the parentheses. So that's really how it works. Here's an example here of a compound where the cation is the ammonium ion rather than a metal ion. How we name these compounds that contain polyatomic ions is pretty simple. You just write the name of the cation and follow it up by the name of the anion, but you don't have to put like the word ion in there. Sometimes there's a little bit of work to be done to figure out the charge on the cation. Remember, we always know the charge on the anion. So a good example of this is these two compounds here. Calcium is 2+ because it's in group 2A, and then nitrite, we know it must have a different charge from calcium because these guys are not combining 1-to-1. Whenever we see ions not combining 1-to-1, we know they have a different charge from each other. As there is 2 of the nitrites, I know that nitrite must have a -1. Now when I move over to this compound, it's a little bit more complicated. I've got iron there, and I know that iron will commonly form either a 3+ or a 2+. And then I've got this guy here, and I'm wondering what the charge is. Now I know that these guys have different charges because they're not combining in the 1-to-1 ratio. I go to my table and I see that the polyatomic ion that is PO4 has a 3- charge. It's called phosphate. Now I've got 2 of those that gives an overall 6- charge. So I must have an overall 6+ charge, and as I've got 3 ions, it's got to be 2+. So sometimes there is a little bit of work to be done to figure out the charges on these guys if you're given just the formula. And that's you need to do that. You need to be able to figure out the charges on your cation when it isn't one of those that has a fixed charge. So when it comes time to naming these guys, like I said, we're just going to give the name of the cation followed by the name of the anion, but you need to be aware that sometimes the name of the cation requires Roman numerals. So this is just named here as ammonium sulfide because we've just given the name of the cation followed by the name of the anion. This is given just as calcium nitrite because we just give the name of the cation followed by the name of the anion, and because calcium is in group 2A, we don't have to specify the charge in Roman numerals. And then when we come to this guy, iron, we already just figured out just a moment ago, has a charge of +2. Because iron is not in group 1A, group 2A, and it is not aluminum, gallium, silver, cadmium, or zinc, we have to put the Roman numerals to indicate the charge in its name. So this guy becomes iron 2 phosphate. So you just got to be aware of when to include the Roman numerals. Notice there are no numbers that indicate how many of each ion are present. We don't do that. right? We don't have to do that at all. So never ever put iron 3 because there's 3 in the formula there. Don't let it might be iron 3, but that's not why we're going to put it there. Okay, so that just concludes this small section on naming polyatomic ions. As I said, the best thing that I can recommend for you is to find a nice extensive list of these that has the names, the formulas, and the charges, and make sure you have that at hand as you're working through the material.